Okay, I'm going to talk a little bit about angular displacement versus linear displacement and angular speed versus linear speed and their relationships. So what I have here is a wheel, and this wheel is going to spin in place around an axle. So it's going to spin around the middle point here. So that yellow dot represents the axle that the wheel is going to spin, and we'll say that it spins this way. I'm going to put a red dot on the edge of the wheel and a blue dot near the center of the wheel. As they spin, and let's say they rotate through one revolution, they're going to travel the same angular distance, which is abbreviated or notated with theta. Okay. Now, if we want to study the linear distances of the two, the linear distance for the red one, first of all, let's take this equation and rearrange it. So we have L is equal to theta times R. And for both of them, the theta value is going to be the same because they rotate together. But the radius for the red dot is going to be much bigger than the radius for the blue dot, which means the linear distance for the red dot is going to be much bigger than the linear distance for the blue dot. Okay, so that's the relationship between angular displacements for those two dots. Okay, now the angular speeds are going to be the same, and angular speed is related to linear speed using this equation. That T stands for tangential. So it's the linear speed that the two dots have. And it is related to the angular speed, which is abbreviated with this symbol, which is a lowercase Greek theta times R. Now, for the red dot, it's going to have an angular speed that is equal to the angular speed of the blue dot. But once again, the radius of the red dot is going to be much bigger than the radius of the blue dot. So the red dot is going to have a greater tangential or linear speed than the blue dot. Now let's say we have a wheel that is rolling across the ground. I'm going to attempt to draw a straight line to represent the ground here. And that's a poor drawing, but you kind of get what's going on. So this wheel is going to spin this way, and it's going to roll without slipping, and it's going to travel a distance of d. So this wheel is going to roll, and it's going to end up at another distance. As the wheel rolls, and I'm going to show you kind of a shortcut here, the linear distance that it travels is going to be L. And recall from a moment ago, L is theta times R. Think of it this way. As the wheel turns one revolution, it turns through one circumference. And that circumference is equal to the linear distance that the wheel travels. Now let's talk about linear speed. A point on the wheel, and I'll indicate that in blue here, is going to be moving with a linear speed. That linear speed is related to the angular speed by an equation I showed you just a moment ago of this. Now, that linear speed is also going to be the speed of the hub of the wheel. So this thing has a velocity vector going that way, and it's equal to the distance times the time, or distance divided by time. Sorry, it's early in the morning. The distance that it travels is going to be equal to its length, the arc length, or the distance that it rotates. So I could rewrite this and say that Vt is theta times r over time. And you should recall from an earlier lecture that Vt is equal to theta divided by time, which is angular speed, times r, which is where we get this. So on the problem on the worksheet where you have the penny farthing bicycle with two different wheels, the linear speed of both wheels is going to be identical, but the wheels are not going to spin at the same rate because of the radii of the wheels. So the rear wheel, the smaller wheel, is going to spin faster in order to have the same linear speed as the front wheel. I hope this helps. Please reach out with any other questions you may have.